I'm going to be teaching you this lesson today. We're covering 13.1 sequences. Um, so let's go ahead and get started. So we have a definition to start. A sequence is a function whose domain is the set of positive integers. Now, we say positive integers, but you may want to get used to thinking about these positive integers as what are called natural numbers. And it's the same thing, right? The natural numbers and the positive integers are the same thing. You're just going to see it called this more often in computer science courses and higher level math classes and whatnot. So a sequence is a function whose domain is the set of positive integers. So in other words, we put in a positive integer, get something else out. Think of the function f of x equal to 1 over x, where x is strictly greater than 0. The outputs of this function represent the sequence f of n, which is equal to 1 over n, for all n strictly greater than 0. Note that n is used to represent the independent variable in a sequence. This serves to remind us that n is a positive integer, and that's what this is telling you right here, right? This is math speak for positive numbers. Strictly positive does not include 0. A sequence is represented by listing its terms in order. In dealing with sequences, subscripted letters are used, such as a sub 1, which would be equal to f of 1, which is the first term, a sub 2, which is equal to f of 2, the second term, and so on out to a sub n, which is f of n, or the nth term. For the sequence f of n is equal to 1 over n, we write a sub 1 equals f of 1 equals 1, a sub 2 equals f of 2 equals 1 half, a sub 3 equals f of 3 equals 1 third, and f of n should be a sub n equals a sub n equals 1 over n equals a sub n. When a formula for the nth term is known, sometimes called the general term, the entire sequence can be represented by placing braces around the formula for the nth term, or, if you're a computer science major, a curly brace. All right, so let's go ahead and get into our examples here. Basically, this whole process of what we're talking about here with sequences, to sort of how you want to think about it, is the same way that we have a function, just to give you a little side, the same way that we might have a function, right? Sum f of x, right? And then this function f of x defines a relationship between the x values we put in and the y values we put out, right? What a sequence does is it defines a relationship between some mathematic definition of a set of numbers and the set of numbers that you get when you start plugging in positive integers. Sort of the same idea. They're basically just another sort of function. All right, so let's go ahead and do some examples here. So we want to write down the first 6 terms of the following sequence. So for a sub 1 is equal to n minus 1 over n, we're going to treat this like a function. A sub 1 will be equal to, we're going to plug in 1 wherever we see an n in this. So you get 1 minus 1, divide 1. This is going to be 0 up top, divide 1. This is just 0. A sub 2 will be equal to 2 minus 1 divided by 2. So that's just 1 half. A sub 3 will be equal to 3 minus 1 divided by 3, which is 2 thirds. A sub 4 will be equal to 4 minus 1 divided by 4. This is 3 fourths. Maybe you're noticing a pattern here already. That's a really important thing about sequences. We use them to talk about patterns in mathematics. Maybe you're seeing the pattern here already. A sub 5 will be 5 minus 1 divided by 5. This is 4/5. And a sub 6 is equal to 6 minus 1 divided by 6, which is 5/6. And maybe you can see here where all we're really doing is we start with a numerator and denominator, and we start at 0 and 1, and then just add 1 to them each time, and then evaluate the fraction and simplify as necessary. So that's one of the uses that we use that we get out of sequences, is to help us talk about certain patterns. All right, number 2, we got b sub n. So b sub 1, again, treating this like f of x, plugging in for every x, right? We're going to plug in for every n. This will be -1 to 1 plus 1 power times 2 divided by 1. So that's negative 1 squared times 2. 1 negative 1 times negative 1 is just 1. So this is 2. B sub 2 is going to be equal to negative 1 to the 2 plus 1 power times 2 divided by 2. This would be negative 1 cubed times 1. So this is negative 1. B sub 3 will be negative 1 to the 1 plus 3 fourth power times 2 divided by 3. Raise anything to an even number, it's going to be positive every time. So this is going to be 2/3. B sub 4 will be negative 1 to the 1 plus 4 is 5 power. Raise anything to an odd power, it keeps the sign you started with, times 2 over 5. So this is equal to negative 2 fifths. B sub 5, it's doing the first 6 terms, okay. Negative 1 to the 5 plus 1 power is 6 times 2 divided by, that's supposed to be a 5. I messed up back there on that other one, huh? Yeah, I added
Yeah,
the
it's.
wrong one.
I was
It's
looking at
supposed to
it.
be
It's
a
supposed to be a
4.
half.
Yeah, it's supposed to be a 4. Okay. So this is negative 1/2. Let's be positive 1 times 2/5. This is 2/5. And then b sub 6 will be negative 1 to the 1 plus 6 is 7 times 2 divided by 6. This will be negative 1 times 1/3. This is negative 1/3. All right. Now this is kind of neat where we have a multi-part definition, sort of like a piecewise function we saw earlier in the semester, right? So C sub 1 will be equal to, we have to take 1 is an odd number, so we have to take the part of the definition that lets us deal with odd numbers. So this will be 1 over 1, which is just 1. C sub 2, we have to plug this into the part of the definition that lets us treat even numbers. So this is just 2, because we just plug it straight in for n, right? C sub 3 will be 1 over 3. C sub 4 is just 4. C sub 5 is 1/5. And C sub 6 is just 6. Okay. Are there any questions about what we're doing here? How we start with a number and just count up to just the whole numbers, just positive numbers, and how we get our results out of the sequence definition? Okay, I'll take that as a no. Remember, it's exactly like the functions we've been doing all semester where you have an f of x and you take some number and plug it in for every x, take whatever the next number is, plug it in for every n, and just count up one at a time. It's that simple. Okay, so our second set of examples is going to be determining a sequence from a pattern. Like I was saying earlier, we use sequences to help us figure out certain patterns in mathematics. Really important. When you do this, sort of the way that I try to approach it is I try to look at the first term that it gives me and the last term it gives me and see if I can figure out some pattern from that. And if it isn't immediately obvious, then I just go to looking at the second through whatever terms are after it, because usually the first term can throw you off. So if you sort of like my checklist to think through these things, the first thing I do is look at first and last term given. And if that doesn't work for me, then I move on to second, look at all but first term, work back to first. Let me show you what I mean by that. So in this problem right here, right, we've got e and then e squared divided by 2, e cubed divided by 3, e to the fourth divided by 4. Now, maybe that pattern is immediately obvious to you and maybe it's not. Let's assume it's not obvious and work from that perspective that it's not obvious, right? I look at the first and fourth term here. I don't see anything immediately obvious between these two to go from here to here other than you raise it to 4 and divide it by 4. But if I look at the second, third, and fourth terms, right, to me, this is kind of obvious what's going on. If I look at just the other terms that are given, we're getting e to the n divided by n, right? And then if you go back and look at the first term after that, right? If we go back and look at the first time after that, we can go to e to the first divided by 1 is equal to e. And then we get the rest of them after that, where we just get e2 divided by 2, e cubed divided by 3, and so on, right? So this set will be equal then to the sequence e to the n divided by n. Okay. Any questions on that? All right.
Show them the thumbs. Give them the thumbs.
Yeah, right. I hope I'm not moving too fast. All right. Okay, let's take a look at number 2 here. So same deal, number 2. Let's use purple. Same deal. I'm gonna look at the first one and the last one given. I don't see anything obvious about what's going on here other than I had to divide something by 1 to get to 127, right? So let's look at these three middle terms. So we have 1/3 goes to 1/9 goes to 1/27. All right. So this is the same thing as 1/3, just what I'm noticing. This is 1/3 squared, and this is 1/3 cubed. So it seems like whatever I have in my sequence, the bottom part is 3 being raised to something, right? So if I have to get 1 out of the first number, right, it seems like the numerator doesn't change. So I think my sequence is this. I think my sequence might be 1 divided by 3 raised to some n, right? Because the top isn't changing at all. So remember, our n's start at 1, right? So n starts at 1. And then the next thing I think is the only way to get 1 if I divide by 3 is if I can make this 3 equal to 0. So, or I can make this power equal to 0 in the first spot. So if my n start at 1, then I want to think, okay, what minus 1 equals 0? Just 1 minus 1 equals 0, right? So then I want to replace one of these with an n. So this gives me that my sequence will be 1/3 raised to the n minus 1 power. And then if we check this, we get 1/3 raised to the 1 minus 1 power, which is 1/3 to the 0, which is 1/1, which is just 1. You get 1/3 to the 2 minus 1 power, which is 1/3. 1/3 to the 3 minus 1 power, which is 1 squared, which is 1/9, and so on. Okay. Is there any questions about my thinking at all and sort of the mental process I went through to work through this? All right. Let me put a question mark in here. Just to, emphasize that this is what I was concerned about. So let's go on to the next one. All right. Now, this is a pretty interesting one because this shows that there's multiple ways to talk about any of these sequences and you can define them in different ways, right? So if I look at the first and seventh power, I add 5 to it. So adding 5 doesn't seem to get me, or the first and seventh, right? So the first and fourth terms to go from 1 to 7. I add 6, not 5. I'm crazy. I add 6 to it, but that doesn't really seem to give me anything. So then I want to look at my interior terms. So we're going 3, 5, 7. So these are all just odd numbers, right? So I could define this as if I start at 1, remember n starts at 1. Okay, well then I start at 1 and I add 2, I add 2 again, and I add 2 again. So I can say that this is equal to the sequence n plus 2. and that's good enough. You're totally done. However, these are all odd numbers, and in mathematics, odd numbers have a very specific definition, right? So the math definition of an odd number is this: 2n minus 1, right? So if you plug in 1 to this, you get 2 times 1 is 1, minus 1 is 1. You plug in 2, you get 2 times 2 is 4, minus 1 is 3. Plug in 3, 2 times 3 is 6, minus 1 is 5, and so on. And this produces all of your odd numbers. The even version of this, you just knock off the 1 and you get 2n. And it gives you all the even numbers. If you're a computer scientist, if you like computer science, it's 2n plus 1, because they start their natural numbers at 0 for some reason. Something to do about computers can't process things. I don't know. But this is sort of the interesting thing here, like I said, that is neat about sequences is that there's a whole bunch of different ways to define sequences, like so many different ways to define sequences. Some of them are real obvious and may only have one. Other ones have all kinds of ways to define a sequence. Okay, let's check out number 4. Does anybody have any idea what number 4 might be? Throw something in chat for me. You can turn on your mic and say something to me. Doesn't matter. Any idea what might be going on with number 4?
I think, okay, if we start with the first term, then, let's see, to the last one, it's 25. So, I was gonna say, like, I was thinking it's like being multiplied, but I, okay, I don't know how to explain my reasoning. Yeah, down the chat kind of looks right.
Okay, so we got one that says n to the n. All right, let's check this out. So 1 to the 1 is equal to 1. 2 to the 2 is equal to 4. 3 to 3 is 27. So I don't think it's n to the n. We got another one that says n squared. So let's try out n squared. I think n squared might do it. We've got n squared. So 1 squared equals 1. 2 squared equals 4. 3 squared equals 9. And there you go, right? This will keep going. So we can say that this is equal to n squared as a sequence. So yeah, as far as the looking at the first and last terms, remember, if you look at the first and last terms and something is not immediately obvious, move on to looking at the interior terms. The only reason why I bring that up is because for me, in my experience as a student, there are some of these sequences that you will see that when you look at the interior terms, you have no idea what's going on. But if you look at the very first couple terms and the very last couple terms, you can see the pattern in there. But it'll be like immediately obvious. And if it's not, move on and just look at the interior terms. For most of the stuff we're going to do, right, that's like a future thing. For most of the stuff we're going to do in this class, I'll give you the hint. Just look at the interior terms. That's going to help you out. Okay, let's check out this last one here. So for this one, I picked the same color I started with. For this one, this is what I'm going to say to do, right? I can see, looking at this pattern, that the 1 over n is sort of obvious, right? We're just getting that every time, right? So we get 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, right? That's kind of obvious, but that only gives us our positive numbers. So we have this simpler one. Let's try to work backwards and figure out how do we alternate this negative sign. Now, earlier, we had this example up here, number 2. Well, we had this alternating 2, -1, 2/3, -1/2, and so on. What part of this is causing that to happen? Anybody?
The exponent.
The part with the exponent, right? The -1 being
Yeah.
raised to something. Cool. So let's go down here and let's check that out. How should we define this then? So let's take a look at what's happening here. Our numerator staying the same, right? Numerator, I can spell, is same always. So that gives us a hint that this should probably be equal to well, actually, no. That's going to be wrong. If we think that way, we'll go down the wrong path. Okay. So what's the bottom going to be? Anybody? It's going to be n, right? So if our exponent up here, right, is what's changing it, if this part that has our exponent, our -1 to the n plus 1 power is changing it, what goes on top then? It's just that -1 raised to something, right? Does it matter if it's n plus 1 or n minus 1?
I don't think it matters if it's n plus 1. Well, because or even it would matter. It'd be n minus 1, right? No.
So both of them totally work. It can be either one, right? Because if you do n plus 1, then your first term is -1 to the 1 plus 1 power. So this is just 1 up top. Your second term is 2 plus 1, which is 3, gives you -1. If you do -1, you get 1 minus 1, which is 0, and that's just 1. You get 2 minus 1. Anything to the first power is just itself again, right? So either of these work. This is another example of how sequences can have multiple definitions. So I'm pretty sure my math lab and all that will only take one of these. So for the sake of simplicity, let's say n minus 1, but then notice either -1 n minus 1 or -1 n plus 1 work. All right. Are there any questions on any of this stuff at all?
Or you could do the even and odd on this, right?
Or yeah, that's true. Or you can do even and odd on this, couldn't you? So if we said, how do they start that up there? We totally could. That makes sense. So if we come down here and we say this, we say that it could be equal to, let's just define it as a sub n, and this will be equal to, what would it be? It would be
It would
One.
be
well, I know what it is. I'm asking them.
yeah. Oh, damn. Okay.
So it'd be 1 over n and -1 over n, right? Okay. And then this is for what? What are our values doing up here? Which ones are negative and which ones are positive? We got 1, 1/3, 1/5, -1/2, -1/4. You probably have -1/6. So it's positive whenever n is odd and negative whenever n is even. So you could also define it like that. All right. Any questions on any of this stuff? On any part of it? How to do it, how to think about them, how to work through trying to define them, any of it? I'll take that as a no. All right.
Everybody go with that? Whoever's here, show me the thumbs. How did Carl do?
Muy perfecto.
I appreciate it.
There we go. There we go. Cool. All right, guys. Well, that's what section was that? 13.1.
13.1. And that's it.
And
That
that's
is-
it.
That is it. It's
That's
very short.
sequences. That's a nice touch on sequences. You won't see those again till what? Calculus 2?
Cal 2. And then as soon as you're done with Cal 2, if you're a computer science major, this will be like your entire life for a year.